shall I start?
Yes, sorry, I was muted. Yes, we are live.
Yes, we are live.
Okay. So hi everyone and welcome to this colloquium in the Latin American webinars of high energy physics. So we're super happy to have today Professor Chee Sheng Fong from Universidade Federal do ABC in São Paulo, Brazil. So Sheng, did PhD at Stony Brook University, and then he had a couple of postdoc appointments. First one was in Italy, in Frascati, and then in Brazil, at Universidade, at USP, Universidade de São Paulo, and now he's professor since like 4 years ago or so, Sheng, at Universidade Federal do ABC.
2.
So we are super happy. 2 only, okay. So yes, the colloquium will, Sheng will tell us about how to cook the matter-antimatter asymmetry of the universe. So, please, Sheng.
So, good morning, everyone. First of all, I would like to thank the organizers for inviting me to give the talk during this pandemic. So, shall I share my slides now? So can everyone see my slides?
Yes, thank you, Sheng.
Yes.
Okay, so today I will talk about how to cook a matter-antimatter asymmetric universe. And so first of all, I would like to give a short introduction about our current understanding of the universe. So our current theory is based on 2 pillars, quantum field theory and general relativity. And then in particular, we have these special model, standard models of particle physics. And then the general relativity, we have a specific model, which has a dark energy content, cold dark matter. And also we need inflation in the beginning of the universe. So on the standard model side, we have when the universe is very hot. This is we have a gauge theory, which is described by this gauge group, the color, the electroweak interaction. And then as the temperature reduces due to the expansion of the universe, then there's a phase transition. And we have the Higgs obtain a vacuum expectation value. And today, we only see the color force and also the electromagnetism. So basically, the weak interaction is broken. So we have a massive weak gauge boson. And then in particular, we also observe neutrino oscillations. When in standard model, neutrinos are exactly massless. That means we have to introduce mass for the neutrinos. So at low energy, there are only 2 possible kind of mass term we can write down. One is we use the same degree of freedom as in the standard model. So we write down the so-called Majorana mass. So this violate lepton number by 2 units. And the other possibility, we introduce another light degree of freedom, the so-called right-handed neutrino. So this is not charged in the standard model gauge interaction. So this mass term conserve lepton numbers, the so-called Dirac mass. So the main difference is basically in the Majorana mass scenario, you can have neutrinoless double beta decay, which is a beta decay without neutrinos. So you violate lepton number by 2 units. So of course, on the cosmological side, there's also many incredible progress, especially about the energy content of the universe. And then this is the menu or the recipe of today. So first, I will trying to convince you that our universe is really matter dominated. And then after that, I'll present the ingredients. And then I'll spend a significant amount of time to talk about the symmetries of the standard model plus the standard cosmology. And then after that, I'll introduce leptogenesis, which explain two puzzles, neutrino mass and also matter-antimatter asymmetry of the universe. And then finally, I will touch upon how to test this kind of models. So this is a brief history of our universe. So it starts with there's a beginning, and then you have to go through a exponential expansion, the so-called inflation, in a very short period of time. And then after that, we have the formation of nucleons. At first, we have only quarks, gluons, and so on. And then they cool down, they form protons. And then in particular, a very important period is when these protons and neutrons, they start to fuse to form heavier elements, but they are still lights, like helium-3, helium-4, lithium, and so on. So this is an important period. All the light elements are formed. And then in particular, I just want to highlight the amount of the light abundance depends crucially on the amount of baryons we have, which is the protons and neutrons that we have. And then this is a number of baryon normalized over the entropic density of the universe. So nowadays we have measured this precise number is based on the primordial deuterium abundance of the universe. So we get this precise number. And then as the universe continue to cool down, then at some point we form a neutral particle. So basically the photons will decouple from the plasma. So when we have only the neutral protons. So when the universe first becomes transparent during this period, so and then these photons has been traveling since until today. We observe them as a cosmic microwave background. And in particular, from the anisotropy of the temperature of this cosmic microwave, and we can also deduce the matter content of the universe. Basically, we can determine the total matter content and also the in part of the matter content, which proportion are the baryons, because baryon will exert pressure. So from this measurement, we also get a very precise value, determination of the baryonic content of the universe. So one incredible or confirmation of this kind of picture is the agreement between these two measurements, which come from a different period and different physics. And then now the question is, are there any evidence of primordial antimatter today? And this is so far there's no evidence. So on a galactic scale, so we do not see antiproton flux, which is what we observe. The antiproton flux is consistent with this kind of secondary production, the PP collision, and then we produce antiproton, and then antiproton we annihilate with other proton and generate gamma rays. So the amounts that we measure today, this is consistent with secondary production. So, and then on the larger scale, on the cluster of galaxies, we also do not see these gamma rays, which is produced from the proton, antiproton annihilation. So there's no this anomalous signature. So on an even larger scale, on the observable universe, there's no distortion on the CMB backgrounds due to these additional photons. So we can, at least in our observer universe, we know that we only have matter and there's no antimatter. So this is today. But of course, if you go back to early times, we have a lot of baryons and antibaryon. But the important thing is this quantity, the baryon minus antibaryon divided by entropy is a conserved quantity. That means this is what we have today. we don't see any significant amount of antibaryon. So this has, if we extrapolate back to early times, they have to be the same number. That means that in the early times, we do have this asymmetry of this order. So the conclusion is we live in a matter-dominated universe. And how easy is it to obtain this asymmetry? In fact, in the early universe, we only need every 10 billions matter-antimatter. We only need one additional matter. So it looks very small, but as we will see later, to explain this excess is not so trivial. So now let's look at in the standard picture. If we start with same amount of baryon and antibaryon, what happens is we have a so-called annihilation catastrophe. Because of course this annihilation will keep happening, but at some point this annihilation will be inefficient due to the expansion of the universe. So they cannot, the chance of them meeting each other is very small. And this happened at about when the temperature of the universe is 20 mega electron volt. So if you do this calculation, we'll end up with 10 to the minus 19 of baryon and antibaryon. And this number, of course, first of all, we don't observe the same amount. Second of all, this is really 9 order of magnitude too small from the observation. So this could not explain what we observed today. And then, of course, the other idea is we can impose an initial condition. We have an initial asymmetry. Now, of course, due to inflation, whatever input, they will be diluted by exponentially diluted. So this idea also, besides not elegant, it also doesn't work. So we conclude that in these windows after inflation and before the beginning of Big Bang nucleosynthesis, we need to have a mechanism to generate this matter-antimatter asymmetry. So what are the ingredients we need? So the ingredients is proposed by Sakharov in 1967. The first one is kind of straightforward. We need to violate baryon number. So after inflation, if we start from 0, we need to violate baryon number such that we can generate a non-zero baryon number. The second condition, we need such that the interactions distinguish between particle and antiparticle. In particular, we need both charge violation and charge parity violation. So why? So this is one very simple way to see. So you can have X which decay in a baryon number violating way to left-handed baryons and right-handed baryon. So if charge is conserved, so we take the charge conjugate, we get this B left-handed but bar, and right we take a charge conjugate, we get the right-handed bar. So the rate will be the same. That means we cannot generate an excess of particle over antiparticle. If Cp is conserved, so this will be transformed to B, anti-B but right-handed, and this will be transformed to anti-B but left-handed. Again, the total rate is the same for the decay to particle and antiparticle. So that means we need to violate both. And then the last condition is we need to deviate from thermal equilibrium. So an easy way to see is in thermal equilibrium, we know all the particles, we have this distribution. For fermions will be plus sign, for boson will be negative sign. So this is either Fermi-Dirac or Bose-Einstein distribution. So since B cannot be conserved, that means that the chemical potential will be 0 because this is not a conserved quantity. So now from CPT, we know that baryon and antibaryon have to have the same mass. So then you can integrate this phase space distribution over 3 momentum. So since mass is the same, this is the same distribution. So you end up with the same amount of baryon and same amount of anti-baryon. So we need to deviate from this condition. So do we have what we need in the standard model? So baryon number violation is there because baryon number, as you see in more detail later, is not a symmetry of the standard model. And especially in the early universe, this kind of violation is in particularly very fast. And then C and CP violation. So basically, standard model violates parity because only the left-handed particles feels the weak force, or equivalently, the right-handed antiparticle feel the weak force. So that means parity is violated, but charge is also violated because if you transform left-handed particle to right-handed to left-handed antiparticle, this doesn't participate in the weak force. So that means C is violated maximally. And then CP violation is also violated. This was due to the unremovable CP phase in the Yukawa interactions. So this was detected later. And in particular, it's due to this unremovable phase is due to we have a 3 generation of quarks. And but unfortunately, if we include this phase, so this phase enter in this so-called Yausko invariant. So although this phase is order of 1, but the problem is we have effectively a type of Jim mechanism. So it's suppression due to the quark masses. So this comes into the calculation of generating baryon asymmetry. So due to this kind of suppression, in the end, we have a number which is 10 order of magnitude too small to a number that we would like to explain. And the last condition is out of thermal equilibrium. So in principle, we can have this kind of condition during the phase transition because we know that electroweak has to be broken. So there's a phase transition between the electroweak symmetric and electroweak broken phase. And then this calculation from this work. So it turns out that this phase transition is smooth because the Higgs mass now we know is right here, no, is 125 GeV. And in order to have the first order phase transition, the Higgs has to be lighter than 70 GeV. Actually 70 something. So beyond that, the transition is second order, is smooth. That means we won't have out of equilibrium condition. And let's look at, I also take this chance to discuss about the minimal supersymmetric extension of the standard model, because we know that the Higgs potential will be different due to the existence of second Higgs doublet. But even in this case, the only survival scenario is when we have a very light top scenario, like right-handed stop. So right-handed stop is basically a scalar partner of the top. So this you come into the Higgs potential, this stop. So basically we need the stop to be below 115 GeV to have a strong first electroweak phase transition. But right now, is essentially this idea is ruled out by the Large Hadron Collider data. So at least in this minimal setup, even in the supersymmetric extension to the standard model, we cannot get a first order electroweak phase transition. But of course, everything is not so set because we know that the universe is expanding. That means that if it's possible that we have certain interactions which are slower than the Hubble expansion rate, and which means that these interactions or the particles which interact through this interaction will not be in thermal equilibrium. So it's possible that we have, if we introduce certain new physics, we can make use of the cosmic expansion to have this kind of out of equilibrium condition. And let's discuss a bit about the symmetries of the standard model and cosmology. So the standard model is dictated by this gauge symmetry. And then we know there's a phase transition. In particular, if we focus on the Yukawa interactions of the quarks and the leptons, we see that there's additional symmetry. We can rotate all the quarks field, is the left-handed quarks and the right-handed up and down quarks, by a common phase. And these terms will conserve this rotation. Of course, the kinetic term will also obviously conserve this rotation. That's why we only focus on the Yukawa terms. Similarly, for the leptons field, if you rotate the left-handed leptons and right-handed leptons by the same phase, this will be a symmetry of the standard model. So of course, this is without neutrino mass. Because without neutrino mass, no, sorry, this is, so of course, now we are talking about without neutrino mass. Once we introduce, and sorry, what I want to say is, without neutrino mass, actually we have more symmetry, because this is a neutrino mass. Without neutrino mass, we can actually rotate left-handed and right-handed lepton fields such that this becomes diagonal. So that means that we can actually rotate each family of the lepton fields. So we actually have more symmetry, because we have 3 modes for each family: electron, muon, and tau. And then in the standard model, so we know that we have electric charge conservation because electromagnetism is not broken today. And in particular, this kind of interaction, which violate the charge, cannot be observed. And there's a bound on the lifetime, which is much longer than the lifetime of the universe. But this is okay, because this is protected by the U1 electromagnetic gauge symmetry. And then we also haven't observed this kind of interactions, baryon number conservation, a violation interaction. So basically, we can have a neutron, which so we have basically what we observe is only baryon number conserved interactions. But in principle, we can have proton decay. So this has lepton number 1. This final state has lepton number 0. So this violate lepton number. So this is not observed. So because this symmetry is not protected by gauge symmetry, in principle, we can violate. So we also have a bound. So this is a lot longer than the age of the universe. So then we also observe that in the standard model, lepton number is conserved. So this is a lepton number conserved interactions. But due to tiny neutrino mass, we have observed lepton flavor violation, because neutrino can oscillate to different flavor. But all these are not protected by gauge symmetry. So what we haven't observed is the violation of total lepton number. For example, here, this is neutrino's double beta decay. So this is a neutron in a nucleus. So they convert to proton in a nucleus. So basically the nucleus change. Then emit 2 electron without any neutrino. So here you have a 0 lepton number. In the end, you have a lepton number of 2 units. So this violates total lepton number. And this cannot be observed. And the lifetime is also weaker than this, but yeah, I did not quote the number. But then this another this process which violate lepton flavor, but not the lepton number. So this is in principle there, because if you calculate with this tiny neutrino mass, but this is very suppressed. So which you cannot see in the experiment. And but what we will see if the energy that we consider is much higher than neutrino mass. So basically, we can consider this lepton flavor as a good symmetry. So in fact, baryon and lepton numbers, they are not the symmetry of the standard model. This is first pointed out by Tooth. Because if you calculate the divergence of the current, baryonic and leptonic current, so they have this so-called chiral anomaly. So basically, they come from quantum correction. So basically, we see that at the Lagrangian level, with classical level, these currents are conserved. But when you include quantum corrections, they are no longer conserved. So if you look at the baryonic charge or leptonic charge, so you look at the variation in time. So you see that they are not zero. So basically, which means that this baryon and lepton charge, they can change with time. And how do they change? So they are changed. They are related to this. Depend on the SU2 gauge field configuration. And it turns out that there's such a configuration where in the vacuum we have many equivalent SU2 vacuum, but this vacuum, so this you can show that is related to a topological charge, the change. So basically, this vacuum, what they differ is baryon and lepton number. So the difference is by 3 units. So if you go from this vacuum to this other, the two differ by baryon and lepton number by 3 units. But the thing is, today, this vacuum, to go from one vacuum to the other, you have to go through this barrier. And then this barrier is, if you estimate, it's about 10 TeV. So this tunneling process is very, very suppressed if you calculate the tunneling probability. So that means today we will never observe this kind of process, baryon and lepton number overlapping. But then it was realized back then, if the temperature of the universe is very high, so basically this kind of barrier will no longer exist. So this kind of process, baryon and lepton number weighting process, will be very fast, and it's proportional to temperature with this weak coupling constant, weak fine structure constant to the fifth power. So that means we see that the symmetry is actually a temperature-dependent concept once we put the standard model into an expanding universe, because the temperature of the universe is changing. So sometimes, for example, baryon and lepton number at low energy is a good symmetry, but at high energy is not a good symmetry because it's violated in a fast way, even if the standard model Lagrangian is not changed. So notice that this baryon minus lepton charge is exactly zero, the time variation. So if you look here, so if you take the difference, because this is the same quantity, so this is exactly zero. That means that in the standard model, this baryon minus leptonic charge is exactly conserved. It's not broken even by the quantum effects. So it's exactly conserved. And then, but then at a temperature we are usually interested in, which is in the early universe. So when this kind of lepton flavor violating process is due to neutrino mass is very suppressed. So essentially the lepton flavor is conserved. So or we can say that we have 3 B minus L charge, because in each direction of the leptonic flavor. So this is the average of baryonic charge minus lepton flavor. This is effectively, we have 3 charge which is conserved in the early universe. So we can represent this kind of B plus L violating process, but B over 3 minus L conserving process with this operator. So you can imagine if as we go from one vacuum to the other, so from the vacuum, you generate 3 quarks and 1 leptons. So you can imagine you have this kind of process keep happening in the early universe. But this operator conserve this charge. They only violates baryon and lepton number, but not the B minus L. And this actually is a perfect source of baryon number violation. In the early universe, we can make use of this baryon number violation to generate a non-zero baryon number. And now I will spend one brief slide to talk about the existence of this symmetry and the possibility of generating an asymmetry. So if a symmetry is an exact, so basically we cannot generate all the time. It's an exact all the time. That means it's not broken. We cannot generate even a tiny amount of asymmetry in the corresponding charge. So so that means, but after it's generated, this existent asymmetry, they can actually protect this asymmetry in the charge from being erased. So they have two roles. So basically we need a slightly broken symmetry such that we can generate this asymmetry in the corresponding charge. And then after that, this symmetry better to be effective again, such that this charge will remain until today. So the early universe is expanding soup of many particles, even in the standard model. In particular, these particles are interacting with each other. So how do we organize this kind of system? Expanding and with a lot of particles. So we use the so-called early universe effective theory. That means we just study at each temperature that we are interested in. For example, we have a model of biogenesis, which occur at certain interval of temperatures. Then we study this regime and see what are the effective symmetries that we have. And basically, how do we organize? One key parameter is the Hubble rate. So to know and its symmetry is there or not. So some interactions, so whether they occur very fast compared to the Hubble rate. So if for the first type, if this interaction is very fast, that means we know that all the particles which participate in these fast interactions, they will be in kinetic and chemical equilibrium. Kinetic equilibrium meaning they have this phase space distribution, the equilibrium phase space distribution. And chemical equilibrium meaning that for whatever particle that they scatter initial to final state, so the sum of the chemical potential has to be equal to 0. This chemical equilibrium condition. So we can also have interactions which occur very slow. So this can be due to there's an exact symmetry in the model. For example, hypercharge. There's no interaction which violate hypercharge. So that means 0. Or we can have some interaction which is suppressed at certain temperature compared to the Hubble rate. So we can get an effective symmetry. So if we have these exact or effective symmetries, we get the conserved charges, right? Conserved nodal charges. The final one is so-called relevant. So when this interaction it can be faster, and then after that it'll be about the same as the expansion rate of the universe, and then it becomes slower. So when you have this kind of transition in between, so we will have the so-called approximate symmetries. So right now the nodal charge is no longer conserved, but they will evolve in time. In particular, we have to describe the evolution of these charges. Let's say starting from 0, then in the end, what they will evolve as a universe expanding until we get some certain final value. So to describe this kind of non-equilibrium dynamics, we have to use the so-called Boltzmann equations. So this is relevant. So in the end, what we need to do is to identify all the effective symmetries. And then in particular, then in the end, what we need is just to describe the evolution of these approximate nodal charges. So this is the way to think of how do we organize this kind of baryogenesis in the early universe. So now I would like to spend some time to talk about the relation between the U1 symmetries and the charges. So given an interval of temperature, so we identify all the U1 symmetries. So for each complex particles, which which means that you can distinguish between particle and antiparticle, for example, complex scalar. And so in the fermions, the wild fermions, so if they are in kinetic equilibrium, we know that they have this kind of a phase-phase distribution. And in particular, one important key point is, although this assumption is not really needed, but this is hold true for all the standard models particles. So for particles and antiparticles, because they can annihilate to be gauge boson. So basically, you know that because gauge boson, the number is not conserved, so they have zero chemical potential. That means the chemical potential of particles plus antiparticles will be zero. That means the antiparticle will have the negative of the chemical potential of the antiparticle. And for any reaction of type 1, which is very fast, as we discussed earlier, we have this condition of chemical equilibrium. And then if some U1 is an effective symmetry of our system, for example, B minus L, then that means that by definition, for any interaction of the type 1, if we sum up the charge of each particle, they have to be summed to zero, because this interaction conserves the charge by definition, because if this is the symmetry of the system, that means we can actually solve the chemical potential in terms of charges, because you can see that if we sum over all the particles which interacts in these reactions, since the charge is conserved, so this sum OI, this will be zero. So that means the sum of mu, all the chemical potential will be zero. So that means it's possible we instead of using chemical potential, we can describe in terms of charges. So these are some constants which are not determined, but we can actually solve it in terms of charges itself. So how do we do that? So basically, first of all, we rewrite in terms of number density asymmetry, because this is things that we are interested in, the asymmetry in a particular species of particle. So in particular, if you calculate this value, we can expand in terms of chemical potential over temperature. And this is much smaller than 1. And this is true because we know that the number density of the particle is much higher than number density asymmetry that we observed today. So it's 10 to the minus 10, this asymmetry that we would need. So this expansion is always good. So we just keep the linear order. So that means we can, now we rewrite the chemical potential in terms of the charges that we have earlier. Is a generic solution. So that means we represent now the number density asymmetry of the particle in terms of only the charges of the system. But we still have this constant. But the trick we would like to do is, now we would like to solve this constant in terms of the charge density of our system. So we can construct the charge density. So U1x. So the charge density will be sum of all the particles which carry this charge, right? And then of course this charge is non-zero only when this particle has asymmetry. So if we sum up, then we put this relation. We have this combination which only depends on the charges of the particles in your system. So this we can represent it as a matrix where the index represent the U1 charges of the system. So if you have 2 U1 charges, you have a 2 by 2 matrix and so on. So now we can solve this constant in terms of the nodal charge density and this J. So this J is completely determined by the charges of the system and then we can put this back in. So this constant is solved. So finally, you see that we have successfully written the number density asymmetry of each particle in terms of the nodal charge of the system. That means for all the, we can have as many species of particle in our thermal bath as possible, but all of them can be represented as a linear combination of the nodal charge you have. So if you have 3 conserved charges, that means this is what all you need to study, how these 3 conserved charges evolve if they do, or if they are conserved, they are 0, it's set to 0. Yeah. So the whole thing is simplified. And so now this is the quantity we are interested in, the baryonic charges. So we do the same thing. We calculate the total baryonic charges. So each, for all the particles which carry baryon number, the quarks, they will contribute. So with their corresponding baryon number. So now we can rewrite this as this form, because we have solved this in terms of only the nodal charges of the system. So that means the baryon asymmetry, it can also represent by the effective charges of the system. So that in this way, all the fast reaction, actually they are resummed. In some sense, they are taken into account in terms of this matrix, which depends only on the charges of the system, of the particle. And then the type 2 and type 3 reactions are also captured by these charges. So for type 2, which means that these charges will not evolve in time if they are so slow compared to Hubble rate. So that means they are constant. So if these charges, this symmetry are never broken, so they are 0, for example. And then what we need to study the evolution with Boltzmann equation is only of the type 3, where they evolve with time or temperature. And so baryogenesis could work. So we can see we can generate non-zero baryon number only if there's some approximate U1 symmetry, such that we can generate a non-zero charges. So now I will go to the example of the standard model. I think I'm a bit behind time, but I'll try to speed up. So for example, we consider this high temperature. We have 4 charges, the hypercharged and the 3 B minus L charges that we have talked about earlier. So now we also have to consider the Yukawa interactions, because the interaction mediated by the Yukawa can be fast or slow depending on the temperature. So this is due to Yukawa, and you insert a gauge boson. So you can estimate this scattering rate, which depend on gauge coupling and Yukawa coupling. And they are proportional to temperature. So then you get, if you want this rate to be in thermal equilibrium, so you can see that the temperature has to be below certain threshold. So for example, if baryogenesis occur in this window, that means all these Yukawa scattering mediated by D, U, and E are not in thermal equilibrium because the temperature is higher. And that's, which means that if we rotate the right-handed down quark, up quark, or electron, so that means because this Yukawa, essentially you can ignore them in the Lagrangian. That means we have this symmetry, rotation of the right-handed the field. So potentially we can have this 3U1 corresponding with this rotation. But actually up and down, they are not symmetry. This is broken again by quantum effects. So this is they have a mixed asymmetry anomaly. So we are end out with in this regime, we only have the rotation of the right-handed quarks. So this has been considered. If we consider this range, that means we have to include U1 in the right-handed leptons. So if we solve for the number of baryon, we have appearance of this hypercharged density B minus L plus the charge density in the right-handed electron. So in principle, if we introduce a model which violate this slowly, we can generate a non-zero these charges and they will be, or we can assume if there's a model which generates pre-existing a asymmetry in the right-handed electron. So hypercharge is not broken. That means we can generally set this to 0. It's never broken until electroweak scale. But then at this below this temperature, this electron Yukawa get into equilibrium. That means this is no longer a symmetry of the system. That means we can only represent into the 4 charges that we talked about. Since this is not yet broken, it's 0. And if our theory never breaks B minus L, that means this has to be 0. So that means you cannot avoid, cannot actually store the asymmetry in the right-handed electron. If your B minus L is never broken. So then you have a standard model plus, I mean some extension. So in this consideration in this paper, they consider B minus L is never conserved charge because it's broken, for example, by this kind of operator. This we'll see later, it's called Weinberg. Then they assume there's a pre-existing asymmetry in the right-handed electron. That means you can represent a baryon electronic charge in terms of a 2 symmetry of the system. Again, this we set to 0 because hypercharge is never broken. But then they assume that after that, this becomes slow. B minus L becomes conserved again. So below this temperature, B minus L is conserved. So we can represent baryonic charge in B minus L and, okay, this is 0. So you notice that B minus L is no longer 0, but proportional to this asymmetry in the right-handed electron. So you can have this possibility. But the key is to introduce this kind of interaction. And also, after that, this should become conserved again. That's a key point. So what are the time we have? So this is another point. I cannot see the chat, but so this is a standard model I so called plus. So again, we extend this to study with additional U1 charges. But maybe I will skip this slide because I still have a more important point to cover. So these are the summary that we have that we mentioned earlier. I will also skip. So now I would like to discuss a Killing 2 puzzle with this so-called leptogenesis scenario. So this is a brief summary. We know that standard model neutrino are massive. At least 2 of them are massive because we know for neutrino oscillation, we know the mass differences, although the absolute scale is not known. And also there's a phase which violates CP. If it's 0, if it's not equal to 0 or pi, that means CP is violated. But of course, the measurement cannot pin down this whether it's violated or not. And then type of neutrino mass. So first of all, if standard model neutrinos are only light degree of freedom, as we have seen earlier, we can only write down the Majorana mass. B minus L is violated in this case. And so since this doesn't conserve standard model gauge invariant, so we can construct the operator which conserves standard model gauge invariant. This is a so-called Weinberg operator. So they are non-renormalizable, and in particular, this require a new physics which come in at the so-called seesaw scale. And if there are more than one, there are more light degree of freedom, which are sterile under, they do not interact under standard model gauge interactions. So we can actually construct the so-called Dirac mass. This is a new light degree of freedom. In this case, B minus L can be conserved. And of course, for standard model gauge invariant, we can have this kind of operator, which is the Yukawa term. This is a renormalizable. Or we can also have the seesaw mechanism at play. So by introducing the new singlets under standard model, or some new doublets, but under some new SU2. This is not the standard model SU2. So this is nice because we can still have the seesaw mechanism to explain the light neutrino mass. But for this kind of mechanism, we need a very, very small 10 to the minus 12 of Yukawa coupling to explain the observed neutrino mass scale. But additional symmetry is required. For example, to if we want to have this mechanism, we have to forbid this term. So normally people introduce new symmetry. For example, this right-hander nu carry a Z2 and phi carry Z2. So you cannot have this operator, you cannot have this operator. And this is naturally, if we have a new SU2 doublet, this is naturally forbid by this new gauge symmetry. Of course, we can also have, in this scenario, so-called quasi-Dirac. That means B minus L is still violated, although by only a bit. That means this Dirac mass term is split into two Majorana states, but these two states, their mass is the splitting is proportional to B minus L violation. And so seesaw mechanism, if you look at the seesaw operator, is nice because we solve the first puzzle. The light neutrino is very light if this seesaw scale is very heavy, because neutrino mass is proportional to the wave of Higgs square over this big scale. And we can also have this operator also break B minus L by 2 units, and we can have a new CP phases in this coupling. And in principle, in this lambda is hidden some new heavy degree of freedom. So in particular, this new heavy degree of freedom can be responsible for generating cosmic baryon asymmetry through the so-called leptogenesis. So of course, the bonus, if we consider this operator, we can have neutrinos double beta decay. So this is just to mention this mechanism is proposed even before the discovery of neutrino mass. And what they depends on, the B violation, where does it come from? It comes from the B plus L violation in the standard model that we have seen earlier, the so-called electroweak spharon interactions sometimes. And this is the windows of genesis we have. You have to be after inflation and before BBN. These are biogenesis windows. And for leptogenesis, since it's realized on these B plus L violation interactions, so it have to happen above 130 GeV. So the windows is slightly smaller. So the dish we would like to cook is how are we supposed to generate this baryon number in this regime before the BBN? Okay, so for the Majorana seesaw model, so at the 3-level realization, as we go above in temperature, above this scale, we can probe into the content of this operator. What is hidden in this lambda? We can have 3 possibilities, fermion singlets, or fermion triplets, or scalar triplets. So these two have SU2 gauge interactions, but this will be completely singlet under the standard model. So we have all the ingredients for the leptogenesis, biogenesis through leptogenesis. We can have this new particle, they can decay. So they can decay in a B minus L violating way to lepton or Higgs, or this can decay into 2 leptons, for example, or we can have a mixture of the cases. And in particular, all these decay can be CP violating. That means the decay to particle, to leptons and anti-leptons is different. The rate occur at different due to the complex phase that we have here. But in particular, we need at least 2 generations of this heavy guy, or we can have only N and phi, because we need a relative phase to have a CP violation. And here, I say it has to be smaller than 0. In fact, we need to generate more anti-leptons than leptons to get a correct baryon number violation. And then we can have a late decay. Late decay meaning that this particle you stay long enough. So when their lifetime is equal to the Haber rate at this temperature, so this temperature is much below their mass. So that means they decay very late. So that means they are out of equilibrium, because you have some overabundance compared to their supposed to be equilibrium density. And then finally, what we have is the baryon number will be related to some coefficient, about 1/3, to the B minus L charges of this is the conserved charges, But since it's broken slightly, so we can generate non-zero charges here. And it's equal to the negative of this, because notice that B minus L, because they have an opposite sign with the lepton number. That's why it actually needs more anti-leptons than leptons to obtain a correct sign for baryon asymmetry. So then this eta capture these dynamics. How late is a decay, for example? So it can be 1 is the most efficient and 0 is a very inefficient. So 1, that means that you can have a super late decay. That means that you don't have the washout. So everything, all the X decay, you'll be responsible for this baryon asymmetry. Okay, so the questions next is, what is the lower bound on this scale? We have upper bound from the neutrino mass. Neutrino mass have to be smaller, and this C has to be perturbative. So but from leptogenesis, is there any lower bound? So I'm way behind time, but I will speed out a bit. But here, I think this is important point I want to stress. There's actually a restriction come from neutrino mass and the required CP violation. So you can imagine CP violation come from the loop correction and the 3 level. So this is a phase. That means this guy have to go on shell in order to generate the so-called the phase for the CP phase. Besides the coupling, and also we need to have this so-called kinematic phase. So if we look at the CP violation for leptogenesis, we notice that there's a neutrino mass diagram hidden under the CP violation. That means the CP parameter has to be proportional to neutrino mass. So if we require to generate sufficient baryon asymmetry, that means we consider the most efficient case, and this is what we need for the CP violation. This implies a bound on the mass scale we need. This is so-called Davidson-Ibarra bound. So this mass scale of this guy, which decay cannot be very, very light. Of course, there's a caveat. So actually, there's another contribution to this CP violation. This doesn't violate total B minus L, but only violate the lepton flavor or B minus L flavor. So if you represent this by the effective operator, this is a dimension 5 operator for neutrino mass. So this dimension 6 is not constrained by neutrino mass. So they come in from here. So what I changed from the diagram is the arrow. So this is B minus L violating. This is B minus conserving. And this operator contribute here. So it's not constrained by neutrino mass. Although this contribution, if you sum over all the flavor, it goes to 0. But this flavor is important because tau Yukawa interaction get into equilibrium in this temperature. So that means we cannot sum over flavor because the thermal bath distinguish a flavor. So this will contribute to the CP violation. And it has been shown by this study that we can actually reduce the scale to 10 to the 6 in the type 1 seesaw model, including this contribution. So okay, another caveat is to say that if these states are not very heavy, in principle, we cannot, they will play a role. In particular, even their decay will play a role, not only the decay of the Ni, which is lighter, Nj. So we have this additional contribution. In particular, if their mass difference is of the order of their decay width, then we can get a super big enhancement in this CP violation. This is from the perturbative bound. We have to be smaller than one half, but in general, they can be they can be much bigger, but still smaller than one half. And in principle, in this scenario, there's no lower bound. It's only lower bounded by before the B plus L interaction freeze out at this temperature. So this slide I will skip. And there are other ways for leptogenesis. For example, if you suppose that in the Weinberg operator, instead of the standard model Higgs, but it's a second Higgs doublet, which will obtain a small wave, small wave compared to the standard model Higgs wave. So you see that this CP parameter is enhanced by this small wave. So you can actually reduce the scale. So you can see the scale is actually reduced. Yeah, basically you can reduce to up to even 10 to the 4, 10 to the 4. And then, of course, you can also think that neutrino mass, instead of coming from 3, it comes from the loop. That means translate to the CP parameter. That means the CP parameter is enhanced by this loop factor. So at one loop, for example, one of the models, so-called scotogenic, where neutrino mass comes from one loop. So the same thing, you can enhance the CP parameter. You can reduce the scale for leptogenesis. And then there's also a very big industry where they are studying light end scenarios. Sorry. So in this scenario, the physical mechanism is completely different. For example, in this scenario, you are having a N oscillation, this so-called the right-handed neutrino oscillation. So in this case, the N is actually at GeV scale, but they start to oscillate much higher than the 130 GeV. So that means they can store asymmetry. This oscillation conserves a total B minus L, but they violate individual B minus L in the flavor N. That means although the sum is 0, but the individual, this doesn't have to be 0. That means the B will be non-zero due to the B plus L violating interactions. And there's also another idea called the Higgs decay. So in principle, Higgs can decay to this GeV scale right-handed neutrino and leptons. So this decay also had to happen above 30 GeV because to generate lepton asymmetry, which can be converted to baryon asymmetry. But this you need a thermal effect to have CP violation. But this, of course, this effect is there. So this mechanism is also possible. And so please interrupt me if you think I should stop, or because I think I'm.
You can start wrapping up.
Sorry. Should I continue?
To start wrapping up.
Okay, I will try to mention with give me 10 minutes for everything. So for another idea, this I will just mention the basic idea. Because we have looked at the Majorana seesaw. What about Dirac seesaw? In this model is also very more exciting. Because in principle you can B minus L is conserved. So the compensating B minus L is actually stored in the dark sector. So it's possible that you can generate together the asymmetry in our sector and also in the dark sector. So you can naturally explain the similarity between baryon and dark matter energy density. So how to test this model? So in the high scale, we can, that means that experiment cannot reach the energy of this operator to see what is inside. So we can at best have this so-called circumstantial or supporting evidence, lepton number violation or CP violations. So I just want to say, usually in the news, they say, okay, they are measuring this hint at non-zero. Of course, as you see later, this is not directly connected to the CP phase for leptogenesis, but still it's very important hint that CP is violated in lepton sector. And then out of equilibrium condition basically impose the upper bound on neutrino mass, which is consistent with cosmology. So basically in the type 1 seesaw, if we look at it, we decompose Yukawa in this is a leptonic mixing which we can measure, and the neutrino mass which we can measure. We still have this high scale parameter. This is the right-handed neutrino masses, and this is the so-called complex rotation matrix. They have three moduli and 3 phases. So all these 6+3 parameter in principle cannot be probed by experiment because they are at a very high scale. So that means that in principle, even if we see some CP phase in this mixing matrix, or we don't see CP phase, it's possible leptogenesis can occur because there are phases in this R matrix. So there's not actually a direct connection. But if we consider leptogenesis below this temperature, we can see that we cannot sum over flavor. That means a U matrix actually will appear here. So that means the phases that we measure can actually contribute to the leptogenesis. But still, to decouple the phases here and here is not trivial, because we have no idea about the phases here. So can we probe all these? In principle, at low energy, we can probe all of them. So this in principle, these two operators will be generated in the type 1 seesaw. Once we have a model, these two are generated from the same model. So we can measure this. This will be in the neutrino mass, and this will come into the so-called deviation from lepton unitarity, because we have these new states. So leptonic mixing matrix won't be exactly unitary. But this violation of unitary will, in the type 1 seesaw, depend on the scale of the seesaw, will be very suppressed. And the current bound that we can bound is very big. That means in order to probe all this, it's probably not so soon to probe this operator, or probably very difficult. So we can also go on more fundamental model where we have more correlation between the parameters. Because we have less parameters, then leptogenesis can be an output or constraint for this kind of models. I'll skip here. For low energy scale, I just want to stress that, which means that experimentally we can reach this seesaw scale. That means we can study this lepton number violation or CP violation in collider. And finally, I will talk about, there's also an idea that we can see the gravitational wave from this B minus L violation. If they are violated spontaneously at high scale, you can generate cosmic string, and this cosmic string will lose energy through emitting gravitational wave. So depending on the breaking scale, we might be able to see it. And this is an idea if this B minus L breaking is still at high scale, but this scalar response for breaking is a very long lived, because they decay only to this light. For this, they consider light right-handed neutrino. So we can have some modification to the signal, to this signal. But still, it's possible to observe. And this is another idea that we have recently about quasi-Dirac seesaw model. So I want to say that in this model, it's also possible to test this in neutrino oscillation, because this is a parameter space which is consistent with biogenesis, and they can be probed for, because this mass splitting, because each as standard model neutrino is no longer Dirac, but they will split into quasi-Dirac state, and this splitting is very small, but they are in the range which is possible to see in solar oscillating experiment or atmospheric. So this is my summary slide. So I will leave it at that. And I will be happy to answer questions.
Great. Thank you very much, Sheng, for this super complete colloquium.
Welcome.
So are there questions from the audience? I can see one from our YouTube channel. So someone is asking whether it's possible to distinguish the three different seesaw models in the near future experiments.
The three seesaw model, let me go back to the slide and mention the differences. So in principle, if this happened at high scale, I would say that it's very difficult to distinguish, because the only difference between these three types of model is this field, they have gauge interactions. So that means the parameter space will be different because they are very close to equilibrium. So you need to have the parameter space will be different. You need to have when the decay has to be faster than this gauge interaction. So basically the parameter space will be shifted, but all this happen at very high scale. So in principle, it's very difficult because the shift is in a high scale parameter space. So it's not easy to, I would say it's not possible unless you you have a realization of this kind of model at low scale, for example, using resonant enhancement, then it's possible if you can produce these states, they are light enough, then of course you can produce them, then it's a different story if they are light enough. And another thing is, of course, at a lighter scale, I just want to add, since this guy carry SU2 gauge interaction, so you can produce them through gauge interaction, as opposed to this single fermion is even harder to produce. Yeah, even though they are at light scale, because it can only depends on the Yukawa coupling.
There's a second question by Marcio. He's wondering about the connection between dark matter and the matter-antimatter asymmetry. So his question is, how much dark matter models can affect these matter-antimatter asymmetries, and that they are important for the models, or we don't even need them at all?
I think this is really a very model-dependent question, because at face value, these two scenarios are not related. But of course, I think one of the idea is usually, because since we observe the dark matter density very similar to the baryon density, baryon energy density. So that's why usually we try to have a model which to link these two scenarios. So one idea that I show on this slide is basically to link that such that when through the end decay you generate asymmetry in our sector, and the equal amount in the dark sector. So if you in the mirror sector, that means you can also have dark baryons and so on. Then in mirror sector, we expect these dark baryons to have a mass very similar to our baryons, which means that today if the asymmetry, they all come from the same amount with number asymmetry. So which means that naturally their energy density will be very similar. So this is one idea to explain this. This is a puzzle, but in general they are not related. So yeah.
Okay, thanks. There's another question now from Carlos Alvarado. He's asking, so if you can go back to slide 43. You're already 43.
Ah.
So he's asking, why do particles go on shell when thermalizing?
Why do particles go on shell when thermalizing? I guess the question is
add thermal masses. Yes, I'm not sure if I understand the question. Maybe Carlos, if you can develop a bit more.
He mentioned slide 42, not 43.
Slide 42, okay.
Yes, 42.
Okay, so about this effect, I guess. So basically, if you do the kinematics, because this, I mean, basically, these two particles cannot go on shell if you don't include the thermal effects. You cannot have because if you look at the kinematics, because this end is very light. But if you include thermal effects, basically, these Higgs and these leptons, basically you can imagine they can get energy from because they interact with the thermal bath. So they can you can have on shell state even in this so-called loop diagram. You can imagine this is we have like the emitting of the Higgs into which absorbed by the thermal bath, and then thermal bath absorb a Higgs which get absorbed. Same for the leptons. So basically, to have these two particles to go on shell, such that we have the CP phase, the kinetic CP phase, we need to consider the thermal effects. Yeah.
Okay. There's another question now from Devasish Bora. So he's saying for quasi-Dirac neutrinos, the lepton number violation must be very small. Do you necessarily need resonance enhancement there, or there is some other way as well to get the correct lepton asymmetry?
Okay, so I guess it's yeah, I'll use the slide that I have in the end. Yeah. So in this case, I guess it's asking about this case. It's true that this is very small. We introduce a small B minus L violation. So that's why, so basically, even if we are at resonance, so this is basically maximal, meaning CP violation, we already consider at the maximal, the resonance. And as you can see, it's still suppressed by this small violation, because in the absence of B minus L violation, this there's no splitting. This will be exactly 0. There's no mass splitting, so you don't have CP violation. So it's true that is suppressed, but the important point is we know what is the CP violation that we require, and in turns this you give a constraint on the splitting that we require. So that's how we get this relation between the splitting and the successful, the parameter space where you can have successful leptogenesis.
Okay. Now, Juber is asking if you could explain a bit more how do you get the quasi-Dirac mass range allowed for leptogenesis?
Quasi-Dirac mass range allowed for this range. I see. If you mention this range, so basically this range is just from okay, there are probably the first question about this range is obtained basically from the mass splitting can be anywhere, but then this is we superimpose the mass splitting on this parameter space, on the parameter space that where we can see that the leptogenesis is successful. And from here we can see that these are the mass range we require for successful leptogenesis. And then now the other question is whether this mass splitting can be observed by neutrino oscillation. And this will come from the, I did not have the reference here, but this will come from the, basically if the mass splitting is too small, smaller than 10 to the minus 18 eV, that means this mass splitting will be responsible, the oscillation length will be very, very long. So this kind of, we can only probe in the cosmology scale of oscillation. But in this mass splitting scale, the oscillation scale will be, it will be the one which we can probe in the solar experiment or atmospheric experiment. So within this scale. But in any case, for successful leptogenesis, for the scale smaller than 10 to the minus 18 eV square, is not relevant anymore because we cannot get successful scenario. But the probe will be cosmological probe. But it happens that for leptogenesis, the scale, the mass splitting scale, which we can probe in the neutrino oscillation experiment, in the solar and the atmospheric.
Okay, thanks. Are there any further questions? Joel, Roberto, maybe?
Yeah, I have a small question. First of all, Sheng, very nice. The colloquium was super interesting. I have a comment. I mean, a question, a doubt about when you mentioned the scotogenic models. In general, the question is, can you produce the same effects, for instance, with models for neutrino oscillation with higher loops, kind of, because if I remember, you can generate neutrino masses up to 4 loops. Let's say the more extreme models. Are those models possible to have the same asymmetry, or
it's possible?
Just...
Sorry. So yeah, it's possible because the thing is at 3 level we don't have this loop factor is directly connected to neutrino mass. But if you go to higher loop, that means because what comes in here is this diagram, which is not no longer a neutrino mass because we have to include the loop factor for neutrino mass. So that means as a result, the CP parameter is enhanced with respect to the neutrino by this loop factor. If you consider a higher loop, like 1 loop, 2 loop, if you go to higher loop, that means actually the scale of n become too low. At some point, maybe become too low that we cannot have successful leptogenesis because the required scale of n has to be so low. Then that means because we know that the decay has to happen before this B plus L interaction go off equilibrium. So probably not so favorable even if you consider too high loop. Maybe 2 loop is okay. Yeah, but 4 loop is probably not so good. And also the mechanism will be more complicated because they are not, they will decay in principle too, depends on the particle in the loop, no? So this is just estimation of what is the CP parameter can get, but in principle it depends on more couplings,
Okay, thanks. Just a very short question because also with the time.
Yeah.
When you mentioned, there were one question about talking about dark matter and generating dark matter also with the same mechanism. Is it possible, because you mentioned here in all the talk that mostly you need U1 symmetries in order to produce global symmetries, but continuous symmetry. Is it possible to generate same kind of effect with discrete symmetries? For instance, in the typical scotogenic, you have a Z2 inside the loops. Can you try to generate kind of similar effect with discrete lepton number or something like that? Or I don't know.
I think this usually, Z2, because usually you use U1 to quantify a asymmetry of a particle. So this is a U1 charges. So Z2, I don't think it is related. You can relate it to asymmetry of the particle. So you can have a Z2 in the model. For example, these two particles can carry Z2, no? So they can be absolutely stable. So but then the thing is when you're talking about the asymmetry carried by this particle, you still think about U1 global charges. So for example, in this case, you can imagine when you are generating B minus L here and some B minus L compensating in the other sector. But since these two sectors, they don't equilibrate. So that means you can think of this, if they equilibrate, you get 0 again. So that means you can think of this quasi-conserved charge as a U1 store here. So as long as if they equilibrate, if they don't equilibrate, basically you have this quasi-conserved charge. We can evolve from non-zero to non-zero, and they will remain there. And if this remain there, and then the standard model charges compensating B as L will also remain. So but Z2 is can be part of the model, but can be part of the model, but they are not directly related to the number density asymmetry or the charge asymmetry of the model.
Okay, thanks.
Any further questions, guys? So if not, I think it's a good time to stop. Thank you very much, Sheng. We're super happy with your colloquium. So before closing, I just want to make an announcement. Yes, is that we'll have a super special webinar on September 30th. So it will be our seminar number 100. So that's why we have a very special invite. It will be Rai Weiss. So if you remember, he's a Nobel Prize laureate. So we expect you guys to attend for this super webinar. So it's September 30th. So in basically a month from now. Okay, so thank you very much, Sheng, again, and see you all next time.
Thanks.
Ciao.